Okay, it's time and welcome in room C. Our first speaker is Nikolai Edeko. I had the privilege to have him as a master's student in Tübingen. He's now a PhD student in Zurich. And the title of his talk is Betti Numbers and the Spectrum of Dynamics. Please, Nikolai, take over.
Many thanks. So, broadly, the problem behind my talk is the following. A dynamical system always consists somehow of two interacting components, the space it lives on and the dynamics itself. If you work in ergodic theory, this is very one-sided because there's only one measure space if you talk to people in ergodic theory. But if you work in maybe differentiable dynamics or topological dynamics, then things are much more nuanced. And so the question becomes, how does the geometry of a space constrain the dynamics you can have on the space? And conversely, what can you learn about the geometry of a space by looking at the possible dynamics that you can have on it? And in the next 25 minutes, I will give you a simple example of how one can use operator theory to answer such questions or understand them. And conversely, also how geometric methods can help you learn something about operators which come from dynamical systems. And as I already indicated, I will be working with some dynamical systems which have a little bit more structure. So they are topological dynamical systems, which are defined in the following way. So a topological dynamical system is a tuple K phi, where K is a compact metric space and phi is a homeomorphism of the space. Everything I'm going to tell you could also be done more generally, for example, for a time continuous case, but the changes are merely notational. So I will focus on a time discrete case, which is also a one parameter case. Okay, let's look at a brief example, which will also be important later on. So we have the one-dimensional torus, R mod Z, and some irrational elements. Then we can define a translation, or we could also say rotation, of this space with this element A. And this then forms a topological dynamical system, a very simple one, but one nonetheless. The system has two important properties. It is, not just one property first, it is transitive, which means that if you start with a one point and you take its orbit, then this orbit distributes over the entire space, so you get a dense subset. And the second important property it has is that it is an isometric system, which means that if you take two different points and you move them with the dynamics, then the distances remain preserved. Okay. Admittedly, this is a very, very simple dynamical system, but it's important to understand this class of dynamical systems because they are like the fundamental building blocks of more complicated dynamical systems. And for that reason, we are going to look at the general result about isometric transitive systems, namely that you can always represent them in a canonical form, you could say. So the theorem goes like this. So if you have a system which has these two properties, it's transitive and it preserves distances, then there already is a compact abelian group G and some elements such that the system is isomorphic in some natural sense to a rotation on this compact group G. Okay. Of course, not every system is going to be of this form. So here we have an example. We look at the two-dimensional torus and we again take some irrational element of the one-dimensional torus, and then we define a map of this torus by saying, okay, we take the first component and there we just do the usual rotation or translation that we already did in the one-dimensional case. But then in the second component, we're going to again perform a rotation, but this rotation is going to depend on the first component. And then one can show that this system is, well, you can show it's still transitive, but it's no longer isometric. So there are, in general, systems will be much more complicated than just a simple rotation on a compact group. However, a general phenomenon that one can observe, and which is very important, is that even if you have a more complicated system, you can often find a a certain part of the system which looks like a rotation. And this we can also see in this example. So if we forget about the second component for a moment, then the first component really just looks like a rotation that we saw already on the previous slide. So if we project onto the first component, we recover a rotation. And the system can be regarded as a semi-direct, or one says skew product of this rotation with something more complicated. Okay, if one wants to make this more formal, one has to introduce what it means to speak of quotients of dynamical systems. And this is the following definition. So if you have two dynamical systems, k phi and L psi, then the second system is called a factor, which is another word for quotient, of the first system, if there is a continuous surjection between these compact spaces, such that, well, the canonical diagram that you want to draw has to commute. Okay. Now, the thing is, you can always find some kind of isometric factors. Sometimes they are trivial, but there always is some isometric factor, and you can show there is actually always a maximal isometric factor. So you have your general system, and you can find a maximal or largest, which is in this case the same, up to isomorphy, quotient of your dynamical system, which looks like a rotation. And so you could say, okay, this is like a very simple building block of my system. If I want to understand the entire system, maybe it's a good idea to first look at this elementary building block. And now the question that poses itself is, if I want to compute what this building block of my dynamical system is, it can't be so complicated, or can it? Well, here you run into a small problem. So the problem is that quotients can be very, very complicated. And to understand this, we will look at some quotients of the unit interval, which is one of the easiest topological spaces you can imagine. So the first quotient that you can come up with is, okay, I just identify 0 and 1, and then I have a circle. Very easy. A more complicated or sophisticated quotient is the two-dimensional torus, which you can realize as a quotient of the unit interval by using space-filling curves. So you observe, okay, suddenly you have a one-dimensional space, but you can come up with a quotient which is two-dimensional. And of course, once you have the idea of space-filling curves, you can also realize arbitrary dimensional tori as quotients, or hey, just any compact connected manifold. Or if you want to be very fancy, you can take the unit ball of a separable Hilbert space with respect to the weak topology. So even infinite dimensional spaces can be realized as quotients of very, very simple topological spaces. So a priori, there's no reason to expect that if you take the quotients of dynamical systems, that they are somehow going to be smaller or less complicated than the system you started with when it comes to the geometric point of view. Okay, but if you look in practice, what happens? Are factors really more complex than the system you start with? And if you look at simple cases, then you observe, no, for some reason, certain factors tend to be less complicated. However, there are unfortunately not so many precise results in this direction. And one of them I'm going to tell you now. This is a theorem by Hauser and Jäger, two people from Jena, not so long ago. And it goes like this. You have a dynamic system on the two torus, which is transitive. So their precise conditions are more general, but for the sake of this talk, I will trace it like this. Then this maximal isometric factor of your dynamical system has to be one of the following three. It can be a rotation on the two torus, it can be a rotation on the one torus, or so the one-dimensional torus, the circle, or it can be the identity on a singleton. And so in this case, you really obtain what you would naively expect. The system you obtain as a quotient is less complicated than the system you started with, which is nice, but it's if you want to prove it, it's far from obvious how you would go about this, given all the examples that I showed you earlier. And indeed, they work in, they exploit some techniques that you have in low-dimensional topology, like Brow's fixed-point theorem and all these kinds of things. And somehow they managed to prove this using a second theorem as a tool. And this theorem is maybe a bit surprising if you look at it first. It takes some time to digest. So the statement is, if you have a dynamical system on a space that is not completely arbitrary, it has a nice topology in the sense that it is locally connected. So every point has a neighborhood base of connected sets. Then factor map onto this maximal isometric factor is monotone, which means that if you take pre-images of connected sets, they remain connected. Okay, and somehow they can use this, this property to prove, using very topological methods, that somehow the maximal isometric factor indeed does not get more complicated. And what I now want to do in the remainder of the talk is to explain how one can interpret the second theorem using operator theory, and how you can give a very short proof for it and understand why this phenomenon happens and when you could also expect it to happen. And then at the end to also come back and show how the first theorem tells us something about the spectral theory of operators that are associated to dynamical systems and how we can generalize it. Okay, the key tool to do that, so far there have been no operators, is Copmanism, which is, okay, my computer disconnected. So, okay, Copmanism. What is Copmanism? I think most people here know it, but I'm still going to explain it. If you have a compact space K, then you can associate to it the space C of K of continuous complex valued functions on it. And this space forms not just a Banach space, but a unital commutative C-star algebra. And also, if you have a continuous function between two complex spaces, then you can associate to it the pull-back operator, which is more commonly known as the Copman operator, which maps from C of L to C of K by composition. Now, this is an assignment which is not quite invertible, but almost in the following sense, which is the theorem by Gelfand. If you have a unital commutative C-star algebra, so you are on the right side, then there is a compact space K and some isomorphism such that your algebra is isomorphic to the space C of K as C-star algebras. And you can go even further and say that more precisely, this assignment that you have defined here is an anti-equivalence of categories. This is a very fancy language in the sense of category theory for saying the following heuristic. So every notion, every problem, every technique that you have on one side, for example, on the topological side or in the C-stars, on the C-star side, you can use and somehow transfer forth and back and thereby exploit functional analytic methods to solve topological problems in topological dynamics, or vice versa. Okay, and one of the benefits is also that we start with maybe a nonlinear system on the left side, and we can obtain a linear system, a linear operator on the right side. Now, how does this help us? Well, this heuristic takes a number of forms. One is the form of a dictionary, which allows you to translate between different notions. Now, here are some examples. For example, if you have a map between two spaces, then it's surjective if and only if the corresponding operator is injective, and you can also reverse the roles. If you have a compact space K and you have a quotient of your space, then this is somehow, if you go to the other side of the dictionary, this corresponds to saying I have not a quotient, but I have a subalgebra of my space C of K. And in a modular isomorphy, you can switch between these two kinds of points of view and the information remains preserved. And if you add dynamics, then you see that if you have a quotient of dynamical systems, then this corresponds to saying, okay, I have my big system K, C of K with the Copman operator acting on it. And the fact that I have a quotient system is encoded by saying, okay, I take a certain subalgebra, which is invariant. And so again, there's a correspondence between quotients of your dynamical system and systems and invariant C-star subalgebras. An important example for this correspondence is the following. So if we have a topological dynamical system, then the subalgebra, there is a maximal isometric factor, and we can ask, what is the corresponding subalgebra? And the subalgebra admits the following description. It is the subalgebra of all functions whose orbit is relatively compact in C of K. Using the Arcila-Ascoli theorem, you can, of course, reformulate this by saying, okay, I take all functions whose orbit is equicontinuous. And then there's a third description, which will be very important for us, which is not quite so obvious, but which follows from the Peter-Weil theorem, and which says that, okay, I take all eigenfunctions of my operator, and I take the linear subspace generated by these. As it turns out, this is exactly the same space, and this is called the Kronecker subspace. Okay, but back to what we actually wanted to look at, a concrete example of how you can use this Copmanism and the Copman dictionary to understand geometric aspects of dynamical systems. So we look at the first notion that we encountered, a compact space that is locally connected. What does that mean in terms, if you look into the dictionary, C of K? Well, if you open a book about topology, then you learn that, okay, a space is locally connected if and only if, well, if you take maybe an open subset, then it decomposes into two or maybe infinitely many other subsets, which are also open and all connected. But this is, of course, not at all true if you have, for example, a totally disconnected space. Okay, and how could you reformulate this in terms of the function space C of K? Well, I mean, it's maybe not so far-fetched to say, okay, if I have here a function that, oh, that was my eraser. If I have maybe a function which lives here, and then it's 0, and then here everywhere it's 0, and then maybe here it lives, and then here it's 0, then I can also maybe decompose my function. And this is exactly what you can do. So, yeah. So you can show, it's not completely obvious, you need to work a little bit, but your space is exactly then locally connected if every function has this decomposition, which is disjoint, and the factors of the decomposition are irreducible in the following sense. So we say that two functions are disjoint if their product is 0, which is rather straightforward, and a function is irreducible if it cannot be written as a non-trivial sum of disjoint functions. This, yeah, I mean, this is somehow from the systematic point of view, this is how you would define irreducibility, but actually a function, you can show that a function is irreducible if and only if the set where it does not vanish is connected. So this is maybe more intuitive at first. And so a space is locally connected if you can decompose a function into functions with whose not support, but the space where they are not vanishing is connected. Okay, and if you use this characterization, then you can come up with the following characterization of monotone quotient. So say you have a quotient of compact spaces, and you take the corresponding C-star subalgebra that corresponds to this quotient. Then you can show, okay, this quotient map is monotone, so it has connected fibers, if and only if you take a function from the subalgebra, you do this decomposition, you can show that this decomposition is canonical, and all the factors in this decomposition also have to lie in the subalgebra. So this is not completely obvious. You need to work a little bit for it, but for time reasons, I will skip the proof. The interesting thing for us is that it's a very somehow straightforward criterion that you can check. Take a function, decompose it, check whether the factors lie in the same subalgebra. And we will look at an example for how one can apply this to recover the theorem by Hauser and Jäger with a much shorter proof. So we have a system on a locally connected space, and we want to show that the factor map onto the maximal isometric factor is monotone. After the translation we just saw, we'd have to take a function from this subalgebra, and then we have to decompose it and show that all the factors in the decomposition already lie in the subalgebra. Okay, what does it mean to be in the subalgebra corresponding to the maximal isometric factor? It means that your orbit is equicontinuous. Okay, then you do this. Okay, so all at once. I thought there was a pause. So you take the function and you decompose it into these parts, which somehow have look something like this. So you take your function and decompose it into the parts that are connected and not non-zero. And then you have to show that all these different individual parts also have an equicontinuous orbit. However, this follows rather straightforwardly from the disjointness. So this is a short computation, but really nothing happens. You just exploit the disjointness of the supports of these functions. And so you see in a very short way that all these functions still lie in the subalgebra. Okay, so what you can take away from this is maybe that you can reformulate even so any property for the compact space and the dynamics on this compact space in terms of the C of k and the Copman operator on it. And sometimes life gets easier because you have more techniques available, or it's clearer what really happens, because here you see why disconnectedness pops up. It pops up because equicontinuity of an orbit is preserved if you decompose a function. Okay, but this was just an example for how one can use Copmanism to prove or reformulate properties for which this might maybe not be quite so straightforward. Now, I want to go towards the spectral theory part quickly and quickly tell you how a monotonicity is actually useful for you. Now, if you talk to people in algebraic topology, you learn about the following theorem. So if you have a quotient map of topological spaces, there are some nice properties. So the top space is path connected and the lower space is maybe not too wild. You don't need to understand precisely what semi-locally simply connected means. If the quotient map is monotone and the spaces are nice, then the induced homomorphism on the level of fundamental groups is surjective. In particular, you get an inequality of Betti numbers, and you don't need to know what the first Betti number is. It's just sufficient to know that if you take the Betti number of a torus, then it equals n. And in this way, you start to see how this weird monotonicity property, this connectivity of the fibers, pre-images, can help you show that quotient spaces are less complicated than the spaces you started with. Okay, you can use this idea and generalize the result by Hauser and Jäger considerably. So here I stated it for a tori of arbitrary dimension, but you can actually put any compact manifold or any finite CW complex here. It doesn't matter. So you start with a transitive system. Then the maximal isometric factor is isomorphic to a rotation of lower dimension. Okay, and unfortunately, I won't have time to do the proof, which is uses some cool tricks, and is very short. I want to skip to the end, since time is a scarce commodity, and tell you what this theorem, which does not contain any operator theory or anything, tells you again if you use a dictionary in terms of the Copman operator. So, and what it tells you is, well, the maximal isometric factor is related to the point spectrum and hence to the spectral theory of your operator. So it's not surprising that you can come up with the following. Say you have a transitive topological dynamic system on maybe a compact manifold, doesn't matter. Then the point spectrum of the Copman operator is a subgroup generated by at most B1 of k elements. And B1 of k is the first Betti number, which somehow counts the holes, the one-dimensional holes of your space. So if you had a n-dimensional torus, this would be, for example, n. And what you see is that you have a relationship between the number of holes in your space and how large this point spectrum of your operator can be. Okay, and with this, I'm already, I think, 1 minute over time, so I will stop here. And if you have any questions, I will gladly answer them.
Okay, thank you, Nikolai, for this beautiful connection between operator theory and algebraic topology. Are there any questions or comments?
I have a question.
Please go ahead.
Where do we learn about the tricks that you left out now?
So there's an article which is on the archive where you can read all the details and the full generality and all of it.
Okay.
So I can also send it to you if you're interested. It's actually very, very neat because it uses the representation theorem that we saw at the beginning, that you can represent the maximal isometric factor and then classification of compact abelian groups and then some methods from algebraic topology. So there are some cool things which enter.
Nice, thank you.
If you have the PDF of your paper, you can put it into the Zoom chat so everyone can download it just on the fly.
Ah, yeah, sure. Do that.
Okay, any more questions?
I would have a very naive question. And
Sure.
Go ahead.
namely, you call this maximal isometric factor. Now, maybe I missed something. At the beginning, you talked about topological spaces, not metric spaces.
So at the beginning, I said that I assume that all factors, all dynamic systems I look at are systems on compact metric spaces.
Ah, metric, okay.
Yes,
okay.
it makes my life easier. You can also do it without the metric assumption. Then you have to speak about equicontinuity, but yeah, it's, yeah.
Okay, thank you, thanks.
I have a question. Can you please show again the definition of the transitive system?
I will,
if you have it.
I think, okay, I have not used the scroll feature here very extensively. Okay, the transitive system, where is it? Okay, very far to the beginning, near the example. Here. Yes, yeah.
You need a point with dense orbit.
Yes, I'm not a part of that group in our laboratory, but mainly my colleagues from my laboratory, they study such things and they are working on manifolds. And I heard just this definition on the seminar of laboratory, and I see that it is the same. So that will be, I think, of very high interest to my colleagues from my laboratory. Will you accept my invitation to give a talk on the seminar of our laboratory one day?
Yeah, I mean, sure, very gladly I would.
Thank you, because, well, I came with functional analysis, and I see my role as a person who brings together this infinite dimensional linear and non-linear finite dimensional. So I appreciate that you agree. That would be really very nice and helpful. Thank you.
Thanks to you.
Okay, more invitations to Nikolai. He already has a standing invitation to Tübingen, but that's not so interesting. Okay, more questions.